All right, there we go. Sorry about that, guys. I couldn't, for some reason, um, join. So I had to like restart my entire Teams, and that's in the fix. So we're ready. Let's do this. So last time what we covered, I'm gonna start the recording. It's already started. Awesome. Okay. So last time what we covered was um, graphs. We started to introduce graphs. We started to introduce how to store graphs. We started to introduce some of the operations you could do on graphs. But it was kind of vague. It was kind of, uh, I guess you could say, broad. We weren't really doing anything that I want to say in depth. um uh, I guess like compared to like what you're going to go into in the course. So today what we're going to do is we're going to introduce a little bit more things to do with graphs, specifically breadth first search, depth first search, right? Because those are the most important things. Those are what she is going to test you on specifically. And that's your ability to actually do breadth and depth first search. So let me just pull up a reference so I'm not completely going off what she's trying to teach you guys. Oh, let me just pull this up real quick. Give me 1 second. Okay, sweet. So, just a little recap. We're going to go over graph. Oh, make this bigger. We're going to go over graphs. What is a graph? Um, Let me start the poll. And this today's poll is just going to be what is a graph? And in your best, I guess you could say, in your best few words, describe what is a graph. And these are going to be recorded and used for tenants. Awesome. So it looks like a lot of you are kind of getting the core concepts, right? We have vertex objects, we have connections, we have vertices and edges, right? That's kind of like that's kind of like the, I guess you could say, most abstract way to kind of represent it, which is great. You guys are understanding like what is going on inside of these graphs. Now let's kind of dive a little bit further in, right? So let's just kind of draw a graph. And this we're going to use to represent cities. Um, and Connections between graphs represent roads that will take you to different cities. So I'm going to get rid of that last one. We don't need it. So we could take this road, we could take this road, we could take this road. We could take this road, take this road, or we could take this road. And maybe we have like another city up here that you could take a road to get to here. And I'll start giving them names. Let's just say this is LA. Let's say that I don't really know any other cities. Let's say this is Seattle. Seattle. Maybe this is like, I don't know, Vegas. Maybe this is Minnesota. Maybe this is Chicago. Um, Trying to think. This is, I don't know, somewhere in Arizona. I'm just gonna say it's Arizona. Arizona. Um, and maybe this is Mexico City. Very, very awfully, I guess you could say, drawn graph, because this is this is not how close these cities are to each other. But you kind of get the point, right? We're trying to model roads. These are roads. So you would have cars driving on these. And you could kind of use this to model your, I guess you could say, drive from one city to another, right? And immediately you might be looking at this and asking yourself, well, how do we actually get from LA to Chicago, right? Maybe you're trying to develop some sort of map application, and your map application has to be able to take you from A to B, right? We're going to call this A, we're going to call this B. And essentially what you have to do is you have to figure out one way that you are going to kind of like go through these until you get to Chicago, right? Until you land in Chicago, and then you know you're done, right? Because you found the path. But you could also consider, well, how do I know that I'm getting the best path, right? What if we added like, I don't know, Kyoto over here, right? You're going to Japan first. There's a land bridge now, Kyoto. What if we were able to kind of add in a bunch of more cities, right? Because this isn't really representing all of the cities. You'd have probably thousands of cities, and you need a good way to get from wherever you're starting to wherever you're going, right? It doesn't make sense to go from LA to Kyoto to Seattle, maybe to Vegas, to Arizona, to Mexico City, back to Arizona, to Chicago, right? That just doesn't sound like a good path. We need to have some way to actually find the optimal path in this case, right? And when we're talking about finding an optimal path, you're really trying to, I guess you could say, figure out the least number of nodes you have to go through in order to get from one node in your graph to another node. And you could think of this in terms of, well, if this is an adjacency matrix, I should have some representation of how to get to all of these places. Same thing with an adjacency list, right? LA has all of these connections, and we could kind of pick one of them and say, let's go with this. So I'm going to start with doing depth first search first, just because I feel like it's a little bit easier to kind of understand. So what is depth first search? Well, depth first search is a recursive algorithm, and it's essentially doing one thing over and over again until you kind of bump into yourself, right? So I don't know, you can kind of think of this, if you guys know of like the old story of like, I'm trying to think. There's like this old Greek story of how this girl got through the labyrinth. She would leave like string, and just kind of like anywhere she turned, she would just like leave the string everywhere. So if she was somewhere, oh, she found her string. She knows not to go back that way. That's kind of the idea with depth first search, right? You're kind of keeping track of where you're going, and then never repeating yourself, right? Because you have no reason to repeat yourself. And the whole idea is that if I explore every single possibility without actually repeating myself, so we're getting rid of that repetition, right? So I'm not going to go from LA to Vegas to Seattle back to LA, right? And if I did, then I'd go back to Seattle to Vegas and then somewhere else. And we're going to kind of exploit that, I guess you could say, property of being able to keep track of where we've been in comparison to everywhere else. So here's what we're going to do. We're going to come up with some sort of, I guess you could say, uh, rule set that we're going to follow. And we're going to take this rule set and we're going to kind of expand it until we find find a path from A to B. And how are we going to do this, right? What do you need in order to perform some sort of depth first search? Well, I kind of already said, if I've been in node, let's call this C, I should never revisit node C, at least from that same path, right? That just doesn't make sense. So essentially what we're going to do, let me pull this up because I don't want to butcher this. breadth first search, in my opinion, is one of the more useful algorithms. I don't want to forget anything, so where is it? Let me just pull up the pseudocode. For all directed edges from U to V that are in G adjacent edges, okay, awesome. So there's one thing that we're going to need, and that's going to be our, I guess you could say, frontier, right? This is, if you take any AI courses, this is what they're going to call it. But the frontier is really simple. Frontier. The frontier is kind of like, you know what? I misspoke. That's breadth first search. We don't need a frontier. We need a visited set. So let me change this. Frontier is similar, but it's kind of like the opposite of a visited set. It's kind of like the unvisited set, so to speak. So we're going to have a visited set. And what this is going to do is it's going to essentially let us keep track of where we've been, just so we don't repeat ourselves. In this visited set, it's just going to be any sort of container, right? This is a container. And what are we doing with this container? Well, let's see. Let's perform breadth first search. So we have some sort of visited set. And we also have a, I guess you could say, start. And a finish. And a visited. So here's what you're going to try to do. You're going to try to get from start to finish. And in order to do this, we have to kind of go through each of the adjacent nodes of start and try to find this finished node. Essentially doing something like this. So first, let's actually just mark our start in our visited, right? So we're going to say start and then we're going to kind of put it into this little arrow, our visited. I'm going to call it V. Visited. And essentially what this is saying is put our start in our visited, mark start as visited. Right, you can kind of think of this as keeping track of a piece of paper, and just kind of crossing things off as you go. And what we're going to do after is kind of relying on the fact that start is a adjacency list. So this would be different if you're not using an adjacency list. However, if you're using an adjacency list, then this will make this will be kind of identical to whatever it is that you're doing. So we're going to iterate. So for each node, I'm going to call it node n in starts dot, I guess you could say adjacent edges or adjacent nodes. Adjacent nodes. Which would be some sort of function to kind of just get every single node from our adjacent, like from our, I guess you could say, list that we're using to keep track of these edges, return these nodes, right? That's what this is saying. And we're going to reference it as node n. First, we're going to say, okay, if n is finished, then return true or return true. In this case, right, there's a few things that you could do. Um, you could keep track of more information than just returning true, right? I guess this is there a path between start and finish? Essentially, like I'm given some graph and I have to tell you whether or not a path exists. That's this problem. And we kind of build on this later, if you guys want me to, of how you'd actually get the actual path between start and finish. So like return the path from start to finish, or what's the length of the path from start to finish. Those are a small modification to this. And you'll see that in a second when we actually do that. We'll modify this in just a moment. Maybe even just implement it in code. Um, anyways, this kind of like this kind of setup is really just like, is there a path between start and finish, right? Because we're not keeping track of anything else. And if we were going to do anything else, we'd have to keep track of more information, right? This isn't enough to do what we're talking about. But anyways, if we find the node n is equal to finish, then we're going to return true, right? Because that's kind of like the base case. Um, Other than that, we're going to say, okay, um, recursively call all of the other nodes in, I guess you could say, n. So if we haven't returned true, if n is not in visited, and then here's where the recursive call comes in. We're going to call DFS on this new node in the same finished with the same visited. So you can see what this is going to look like. We're going to have n. It's an awful n. Let me fix that n. We're going to have n. We're going to have finish. You could even return this because here we're returning true. This would actually be like return. In finish visited. So you can see that if any point we find the path, we'll return true, and then we'll escape. And then your base case, right? I'll write that down here. We'll just return false. Path does not exist. And there's your DFS algorithm, right? It's as simple as that. And that's kind of why I like it so much. It's because you really just need to keep track of some visited set. You just need to keep track of what node you're currently at. This is kind of not really like a start, but more of like a current. And this is obviously going to stay the same the whole time. So let's actually perform DFS on here. So I'm going to try, I'm going to make some stuff smaller so that I could actually have some space to do this. But we're going to go through something that she'll probably ask you to do on some exam. And let me just move this down. I don't really need that. Anyways, so let's kind of go over what she's going to ask you to do on an exam. So one thing she might say is perform DFS on this graph starting at point A, and always go to the leftmost. So go from left to right when you explore. So what will that look like? Let me stop real quick before we actually do this. And let's just make sure that there's everybody. How are we feeling? I have a quick poll question. How are we feeling about this so far? Before we actually move on to some questions that she might ask you. How do we feel about this? Doing okay. Not great. I like how you didn't say bad. Not great. Okay, good. Well, if you're feeling not great, definitely mention what in the chat I could kind of go over more, and kind of explain. I know this could be extremely confusing. It wasn't the most intuitive thing the first time I learned it, so. I don't understand how we know to go left or right. That's a very good point. In an exam question, she would tell you to go left to right. So and we can kind of go over what kind of questions she would ask you. You could kind of see the graph, so you could kind of assume that you know to go left, right? If we're here, you know to go to the leftmost node first before you go to like there. Think of it like clockwise. Go clockwise. How do we determine which node it travels to first? Is there a particular list order, or does it not matter much? It depends. So in her exam questions, she's going to tell you where to go, right? Because she's going to have to match your output to her output. At the same time, though, when it comes to actually implementing this algorithm in practice, you're just kind of iterating through a list. So whatever the order of the list is the correct way to do it. I guess you could say. In this case, we're going to assume that the leftmost node is the first node in the list. So in practice, no, it never matters which way you travel to first, unless you're building like I guess you could say like a maze solving algorithm, right? Because depth first search is actually used to solve mazes. If you're trying to solve a maze with depth first search, you probably want to always go in one direction all the time. So, and that's something you can kind of encode into your maze solving algorithm alone. Don't necessarily worry about what I'm saying right now, just because it's like it's one of those things that you definitely don't need to know for this class. It's definitely outside of the realm of this class. But if you have like the grid that we were talking about last time, where all the nodes are kind of like laid out in this like the grid way, right? And how we said that the space complexity for this is OV, only because at all of your nodes, you're having a constant of 4 for each node. So this kind of like, if you have some constant, right, I could kind of eliminate that constant out of my graph. And now you're kind of like in this special like graph known as like a grid. At least that's what I call it. And here, right, you could label each of these connections: left, up, right, down, or WASD, or so WASD, right? Something like that. Maybe like that. All I know is there is a way to do that in like an actual algorithm, but you don't have to do that when it actually comes down to like a project Definitely, though, when you're doing these questions, she will tell you where to go. And if you want to know why she's going to tell you where to go, it's because she needs to know that you're not just like, oh, like picking random places to go, and you actually understand the DFS algorithm. So let's kind of do this. We're going to have a stack. Let me pick a different color, maybe red stack. In here, I'm going to call this the visited, like the in order visited list. So in order visited list. And you can kind of think of every time we go to a new place, we're going to print out whatever that place was. So assume that every time you visit a node, you're printing out that node as well. So here, if we go to Kyoto, we're going to print Kyoto. And then here, if we go to Vegas, we're going to print Vegas. So let's actually work through this algorithm. This is an exact question she'll put on your exam, by the way. So in LA, we're always going to go left. So we can kind of think of it as like the clock, right? You're always going to go in that clockwise direction. So LA, I'm going to grow the stack down, by the way. I know that might sound weird. I'm just going to put an arrow. That was an awful arrow. Let me redo that. We're going to grow the stack down. So we're going to push LA to the stack just as like a way to represent the recursive nature of this algorithm, right? Because you could think of what recursion is. It's kind of just like a stack. You're always pushing something to the top. And then as your recursive algorithm is finishing, you're popping off and then you're finishing the work that you haven't done yet. Very similar to a stack, right? If you want to think of recursion, relate it to a stack. If you want to think of a stack related to recursion, maybe it'll help you understand what you're doing a little bit better. But first off, we're going to pop LA from the stack. So we're going to pop LA from the stack, and we're going to travel to each of its nodes. So let's do that. So popping LA from the stack, we're also going to print it. So print LA. And then we're going to push all of the children, or recursively call all of the children in this piece right here. So is N our finish node? No. Is N not in visited? Yeah. Kyoto's not in our visited set. So let's actually call our DFS algorithm on Kyoto. So what is that going to look like? We're going to push Kyoto to the stack. So now we have Kyoto on the stack. And now you got to see that we're going to actually do this algorithm from Kyoto as well. So while we're in Kyoto, we're going to go to Seattle. So let's actually run through how that works. So first, let's actually mark Kyoto. I'm going to mark them actually in this graph. I'm going to mark things with a yellow thing through them. So mark it as visited. So we're going to mark Kyoto as visited. And then we're going to essentially go to all of the adjacent nodes, right? So like we said, left to right, we're going to end up going to Seattle. But before we go to Seattle, we have to pop it from the stack. Just because like recursion, it's going to get popped from the stack. Actually, I should say something more like this. We're not even going to pop it from the stack yet. And I'll show you why later. Let's forget about popping things from the stack and let's just focus on building out our stack for now. Apologies if that's a little confusing. You'll see why. You'll see why when we come back. Don't worry. But Kyoto, we're gonna mark it, and then we're gonna push Seattle to the stack. Seattle. So we're pushing Seattle to the stack. Calling DFS on Seattle. So now we're in Seattle. We're going to mark Seattle as visited. And then we're going to go to each of the adjacent nodes for Seattle. In the first adjacent node, right, to the most left node to Seattle would be, I guess you could say, Kyoto. But Kyoto's already been visited, right? So we're not actually going to go to Kyoto. Right? Because we're going to call this on only visited nodes. only unvisited nodes, I should say, because when you come down here, you could think of Kyoto as like a visited node, right? It's inside of this set, right? Because I know that because I marked it here. So we're gonna not call DFS on Kyoto again. We're just gonna kind of leave it, and we're still here. So the most left node would be Kyoto, and then if we go kind of in that like I guess you could say clockwise, we're gonna get to Vegas. So is Vegas in our visited set? Well, we haven't marked it yet, so no, we are gonna just take the Vegas, right? Vegas would be N in this case, and we're gonna call DFS on Vegas. So how are we gonna represent that? We're going to write it to the stack. So let's add Vegas to the stack. Vegas to the stack. And we're also going to mark it, right? Because we're going to enter this function, right? We're going to add Vegas into our visited set, mark it. and now we're going to start by looking at LA, right? And we're going to start by looking at LA because it's the most left node. But like I said, it's visited, so it's never going to call the DFS in this case, right? Because we know we've already been there. We've been to this entire kind of section of the graph. And we don't even need to know that. We just need to know that Vegas, like when trying to go to LA, LA has already been visited before. So don't revisit nodes you've already visited. That's the whole idea of DFS. So we know that that's been visited. And then we maybe might want to try Seattle because it's also to the left, and maybe that's visited. So at this point, we've been to all of the left nodes, and now we're going to kind of loop around. So you're going to see Minnesota. Now, Minnesota is, I guess you could say, I'm trying to think. Minnesota, I'm going to try to add that. It's all the way up here. Minnesota is not in our visited set. So what are we going to do? We're going to call DFS on Minnesota. What is that going to do? Minnesota. We're going to add that here. So now we've added Minnesota to our stack, meaning that we've called this function with Minnesota as an argument. And now we're going to add Minnesota to our visited set, right? You can kind of see where this algorithm goes. I'm trying to walk through it as slow as possible, but you can see where we're going to go, right? We're going to go from Minnesota now. And Minnesota only has one other connection, and that's Chicago. So we're going to go from Minnesota to Chicago. And in this case, right, obviously we mark it. We're going to append Chicago to the stack. And in this case, Chicago is actually our B, right? We said, how do you get from point A to point B? Well, I'll put that here. A to B. How do you get from point A to point B? Or not even how. Can you get from point A to point B? Well, the answer is you can, right? Because in this case, right, N would be Chicago because we've traveled from Minnesota to Chicago. In this case, marking Chicago as visited, by the way, right? You wouldn't not mark Chicago as visited just because it is your finish. But now, right, we're realizing that I guess it is finished, right? I kind of messed up on this case. In the case of Minnesota, we would have Minnesota, we'd call this on Minnesota, and then we'd see that you could travel to Chicago. In that case, you wouldn't even mark it as visited. You just finish here. So if that makes sense, I know that was kind of like a quick mishap, right? In this case, we're looking for if the node is finished inside of our I guess you could say traveling loop. That's what this is. This is like nodes that we're going to travel to. This is like that section. And in here, we're looking for the finish. So if we found the finish, then we'll return true in here. So we never actually call this function on Chicago. That's important to kind of see. You can modify this algorithm too to kind of put if start is finish, right? You can do that. So now you're calling it on there, and then have like that like as a base case. In this case, the only base case is like the base case is in the loop, and that might be confusing and also not as good. Really, I don't know if it would even be as good. I just know it doesn't make sense to have a base case inside of a for loop. You might want to move this outside, so like more like up here. But anyways, in this case, right, we're going to return true. And the recursive property, I don't know what this is. Hold on, why did that get put? We're not even going to call this on Chicago. So you can think of it like this. We've kind of expanded a whole bunch of nodes on the stack. But what's going to end up happening is something like this, right? I'm going to use blue to represent that one node is returning true or returning something in this case. And what are we returning? We're returning true. So Minnesota is going to return to Vegas true. And then Vegas is going to return to Seattle true. And then Seattle is going to return to Kyoto true. And then Kyoto is going to return to LA true. And LA is going to return to whoever called the function true. And that's kind of what's going to happen, right? And in this case, right, you're going to call every single possibility in the list before returning false. And the reason for that is because you're only going to end up at false if every single possible path has been called. And how do we see that? Well, let's kind of take a step back. And let's actually try to get to a different place. Maybe a place that's not necessarily accessible. So I'm going to temporarily move Chicago. I know we were looking for Chicago. But you remember that land bridge I said that you had to Kyoto? Well, Hawaii. Hawaii doesn't have a land bridge, sadly enough. And when you punch into Google Maps that you're trying to go from LA to Hawaii, and try to find that route, maybe Google Maps is going to do something like that for a search. So we're going to continue out the rest of this algorithm looking for Hawaii, even though there's no land bridge and no way to actually get there. So we're going to add Chicago to our stack, right? Chicago. And then we're going to add Arizona to our stack. And then we're going to add Mexico City to our stack. And then once we've gotten here, you can see that there's nowhere else to go, right? We've kind of lost ourselves in this never-ending path to Hawaii. We don't know how to get there. And at this point, we don't have anywhere else to go, and we're going to return false. And what that's going to do is essentially something like this. I'll point out one fault in this algorithm. I'll correct this. Just because if you noticed, this isn't necessarily true. Maybe you have some sort of variable like found. Let me change this. I'll call it found. And then if found, return true. So the only way we're going to return false is if there is no other way to get there, right? In the other case, we were kind of returning the first time we failed. But in this case, right, we're going to try all the possibilities before we actually return false, right? Because we might have one of these return false, but if any of them return true, we'll return true. And that's kind of that whole idea. Please let me know if that makes sense, or if it doesn't. Please let me know if it doesn't make sense, because that was kind of like the sword piece of this algorithm that I put in here, right? If we found a bad path, we'd immediately kind of return that all the way up. So that was one thing that we have to kind of modify in order to actually get this to work correctly. Doesn't look like anybody has an issue with that. So let's kind of look at what's going to happen for Mexico City, right? Mexico City is going to go through all of them and return false. So we're going to return, we're going to do red. So Mexico City is going to return, maybe not red, maybe like maroon. Mexico City is going to return false on Hawaii, right? We're doing this for Hawaii. We already kind of said what would happen with Chicago, but now think about Hawaii. So Mexico City is going to return to Arizona false. Arizona is going to return to Chicago false. And Chicago is going to look around and be like, oh, I don't have anywhere else to go, so I'm going to return to you false. Minnesota doesn't have anywhere else to go, so it's going to return to Vegas false. Vegas tries to go to Arizona, right? Because we went to Minnesota first, but we realized that path was bad. So now we're going to try to go to Arizona in this case, right? And you can kind of see why, right? We're going from left to right. We go to Minnesota, right? We go to Minnesota, and then we go to Arizona. And we're going to find, though, that when we go to Arizona in this depth first search algorithm, Arizona's already been visited, right? So we're not going to end up going to Arizona, actually. I should say, we're going to, I guess you could say, iterate. So N was Minnesota. We're going to return from that, right? We're returning false from Minnesota. And then we're going to immediately start this loop over again. And we're going to come into here and check to see if Arizona has been visited. And it has, right? We can't go to Arizona because we already been there. And we know that there's no path there from Arizona. So we're going to return back here after doing that check to realize that, there is nothing else. Vegas is going to return false as well. And Vegas is called by Seattle. And Seattle, right? Seattle called its search on Vegas first as well. And then because of that, it's going to have to try to call it on LA too. So N will become LA. And LA is not the finished node. And LA is already visited, right? Because of this visited set. We already marked it. And then from there, we're going to return again, right? We're going to return back to Kyoto. And Kyoto tried to explore Seattle first and realized that Seattle had no path for it. So it's going to do the same thing with LA, except like I said, LA has already been visited. So it's going to return false back to LA, and LA now has nowhere else to go except for Seattle. But Seattle's already visited, and LA is also going to try the same thing with Vegas. But Vegas is already visited too. So you could kind of see that after running this depth first search, we've already visited everything by the time we get back to this base recursive call. And because of that, we're going to have to return false. And that return false is going to go up the chain to wherever we call this, I guess you could say, this call. And like I said, Hawaii, it makes sense because there is no nodes connected to Hawaii for it to actually be able to find it. right? We have no land bridge to Hawaii. And because of that, we're not going to find it in our algorithm doing depth first search. So what are like the key things to kind of take away from depth first search? It's very, I guess you could say, recursive. That's kind of why I put this stack here. That's why I have these arrows and the return values. You're gonna have to rely on either some version of this for whatever what is it called? You're gonna have to rely on some recursive version of this. Like I said, your stack data structure is, I guess you could say, a very recursive data structure. So we could kind of look at this kind of like pseudocode, right? I tried to kind of come up with something similar. But you could kind of see that it's the same idea, right? We have some recursive function calling on this, I guess you could say, function, and because of that, you kind of have that property. And then when you come here, right, how do you actually implement it in just a little algorithm without recursion? Well, you need some sort of stack, right? And you're pushing these nodes to the stack, and as you're kind of, I guess you could say, as you're kind of running through this algorithm, you have to pop from the stack and then discover all of the places that haven't been pushed. And what that means is you're going to push all of the nodes in some order, right? In fact, if you memorize this, or if you just kind of have that in your head, when you get this question on her exam, it'll be really easy. I'm trying to think. We don't really have enough time to go over DFS. So I guess what I'm going to do this weekend, just because I know last week we didn't have anything, I'm going to go ahead and post the DFS version of this to my YouTube for anybody who wants to go over DFS. And so next week we could actually start going into Dijkstra's algorithm. So if this confuses you, definitely reach out to me. Or you could kind of let me know now if you want me to kind of cover anything else about this or address anything. If any of this doesn't make sense. But like I said, I'm going to make a post right after this kind of detailing where you could find all of this material. So if you want, definitely reach out to me about this. But otherwise, do you guys have any questions? The worksheet says do a BFS and do a DFS. Let me peep the worksheet real quick. Data structures. What worksheet was it that you guys were working on? Worksheet 19. Awesome. Okay. Let's pull that up. Worksheet. Then you pull this up. Okay. What are the time and space complexities for BFS? What are the time and space complexities for DFS? Well, you could think of them as being the same. And the reason for that is because DFS and BFS are similar in ways that they're unique. What I mean by that is we're exploring nodes, and we're exploring nodes relative to the number of connections. So you could think of it as kind of like O of V plus E, right? Because you're gonna try to explore at most V nodes on E connections. So if you have V nodes in your graph and E edges, you're only going to explore at most V nodes through E edges. So you take the addition between them, and that becomes, I guess you could say, your time complexity for this. The problem with breadth first search and depth first search is that as you get more nodes and as you get more edges, as your graph becomes bigger, you're going to be doing a lot more searching. And you could kind of think of it as like it's almost O of n squared in a sense that as your graph gets bigger, your nodes, your edges and your nodes, I mean, they might increase linearly, but your edges might increase exponentially, right? Because like I said, with kind of like the where is it? Obviously this isn't like necessarily the case, but as you have more nodes, you're gonna have more edges, like trivially, right? And you could kind of think of it as like the bigger the graph, the longer it's gonna take to do breadth first search, right? Because most graphs tend to be in the style of having more nodes, having more edges based on the number of nodes. And obviously that's not necessary, right? So it's obviously a limitation of your V and E. But if you want to think about it more intuitively, it's going to increase the most based on the number of edges, just because the more nodes you have, you're most likely to have more edges in your graph. Or you have a very sparse graph and your vertices are the ones that take over. Find the DFS and BFS for the following directed graph, right? You could kind of do the same thing, right? Pick a path to kind of explore, right? Maybe left, maybe right, maybe north, try north, northeast, east, southeast, south, southwest, this way, if that makes sense. So like kind of like following the clockwise starting at north. And then that'll lead you here, right? Then here, and then here. And then you can't go anywhere from here. So you go back here, and then you go here, and now you're going downwards. So you try to go here, you realize you've already been there, and then you try to go here, there's no connection here, you end up going here. You can't go back, so you end up going here, but you've already been there. And then you go here, and there's nowhere to go, so you come back here, and there's nowhere to go, so you come back here to realize there's nowhere else to go. So then you come back here, and then you come back here, and then you travel along this edge, right? We're just kind of going in that clockwise pattern starting from north, but you already been here. So then you go south, and now south, like I said, you'll go east, you already been there. You go south again, and now you're trying to go north, can't go north, but then you go northeast, realize you were already there, and then you go east, realize you were already there, but now you have nothing else to go to. So you could see that you would finish on 6. If you want, I could kind of take a picture of this real quickly, and embed this into the, let's do that. Snip. I realize me hovering over like different things with my mouse probably isn't the best way to kind of go over this. So let's actually like. Why is this so challenging to extend? Let me do that. Awesome. Okay. Paste that into here and make it a little bigger. So what are we actually doing? Let's just assume that we're going to go north, northeast, east, southeast, south, southwest, west, followed by blah, 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 west, followed by northwest. And then you go back at north, right? So we're kind of going up this kind of like in that like vertical expansion pattern. So let's do it. You can't go north, can't go here, but we can go here. Can't go here, can't go here, but we can go here. Can't go here, can't go here, can't go here, but we could go here. Can't go here, 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 can't go here. So we'll come all the way back up, come all the way back up. And then we realize can't go here, but we can go here. And then we try to go back up. We go here, realize that we've already been here, so we come back. Can't go here, but we can go here. And then we do the same thing. We can't go back up. We can go here, but we realize we've already been there. So now we go here, and we do the same thing. You can't go anywhere from here, right? This is kind of like a terminal state. So we'll end up coming back here. Oh, looks like somebody had a question. So then there technically more than one way to do this problem. Technically, yeah, there's infinite. I guess not infinite, but like think of all the ways you could expand these nodes in some order. I could have started going downwards, and you would have had a different expansion, right? So I'm kind of establishing that this is the way I'm expanding nodes. I'm establishing that. And now, right, after establishing this, we're kind of like, okay, we ended up here, we're coming back here, come back here, we'll come back here, and then we'll come back here, right? You can kind of follow it, right? Because like that's like the way it would expand. You're back here, right? You started going there. Now we're coming here. Realize we visited this already, so we'll come back. Now we'll go down. And now we're down. Can't go here, but we can go here, but we visited, so we're coming back. And then we're going down. We'll try to go here, can't go there. But then we go down, realize can go up, we can go here, but we've already visited here. So now we'll go here, we've already visited here. Can't go here, can't go here, can't go here, can't go here, can't go here. So you end up finishing. And that's kind of the whole idea of the algorithm. Maybe you'll come back here and finish trying to go all of these places too. And then back up here, you'll try to go to all of these places too, and realize, you know, you made one giant sun. Obviously, keep track of the nodes that you visited and the order that you visited them. So you started with 0, 0, 1, 2, 5, 4, 7, 8. I could just kind of see that, right? We went back to 4. So we went back. So here we went back to 1, down to 4, down to 7, down to 8, and then we went back to 0 to 3 to 6, and now it's the finish. So this is how we expanded our DFS. BFS would be different. We didn't really cover DFS today, but you'd be doing something similar, right? 0, 1, 4, 3, and then you'd kind of have to expand, well, whatever the first node you expanded, so 2, right? You'd add 2. BFS is the same thing, except you have some sort of queue, right? So 0, cost 0 out of the queue, add 1, 4, 3, cross one out of the queue, add two, and then so on and so on, right? We'll go over this next time. But that's kind of like how you would approach this. But we did run out of time. So what I'm going to do is if you have any questions about this, feel free to ask me. But yeah, I could, if there is something specifically that you need help with on this, definitely reach out to me, from my email. Because then I'll see that. I know some students try to reach out to me over Canvas. Don't do that. I don't ever check Canvas. I have so many things on Canvas, so like I don't actually, like I don't see the notifications on there until like a month later. And when I'm like actually going over like the grades that you guys have for like project 3 or project 2, right? Like I don't ever really see stuff on there. So if you do need to reach out to me, reach out to my email. But anyways, yeah, I'm gonna call this here. I'm gonna stop the recording. If there is any other questions.